Hello everyone, my name's Quackmero, and today we're going to be making a very simple autonomous together and for FTC programming. And some of y'all might already know how to make a teleop. Well, there's the first section of FTC. Well, during an FTC match, the first 30 seconds are the autonomous match, and oftentimes these first 30 seconds can possibly be a deciding factor between winning and losing. So having an autonomous really gives that advantage. So here I'll show you guys how to make a simple step-by-step autonomous. First, of course, we're going to go to our team code, the Java, right-click, new, Java class. Let's call it autonomous. Okay, you see it right here. First thing we're going to do is, just like in the teleop, we're going to do extends. Now, we're not going to do op mode. This time we're going to do linear op mode. Oh, yep, right there. Okay, so just like in the teleop, the first thing we'll do is extends. But instead of op mode, we're going to do something a little different. This is called linear op mode. Enter. Now, the difference between linear op mode and normal op mode, oh, right here, is that op mode has two functions. It has an initializing function and it has a looping function. Basically, it initializes and maps hardware and then loops the functions again and again. Mainly used for teleop, but could also be used for autonomous depending on how you make it. But in this case, in autonomous, we're going to use linear op mode. And I think y'all can guess what this is trying to say. Basically, it's going to read the code from up and down. Let me explain it to you. Let's say I want the robot to move 500 inches. And then it's going to move on to the next step. Move or turn 200 inches. And then, let's say, strafe 10 inches. So it's going to read these from up and from all the way, from the very top to the very bottom. This is basically what we're going to be doing. It's, you're going to be giving steps one by one, and the robot's going to be doing them one by one. So the process is a little different, but it should be relatively the same. Let's just do an at. Remember, make sure you stamp that this is an autonomous, because when you, if you forget this line right here, let's say you forget it, when you start your code, or when everything, let's say we finished all of this and you forgot this at autonomous, it's not going to pop up in your autonomous section unless you specifically specify it to be an autonomous. So moving on from that, we're going to make our motors. Private easy motor. We're going to abbreviate things, so upper left, so UL. And this is something you can do. Put a comma, and you can actually put another motor. Upper right, comma, oh, sorry, lower right, and lower left, and semicolon, yep. And like this, you've made 4 motors in one line, and that way you don't have to copy and paste and type things over and over again. I'm just making shortcuts. We're gonna make public void run up mode, and it should here. So a linear up mode basically just works in a singular function. It runs up mode. Inside of run up mode, we are gonna put wait for start, and basically anything, well, no, if op mode is active, There. Okay. So now, how this function is going to work is it's going to wait until we press the start button. And then if we press the start button, it's going to activate op mode. So anything inside of this if statement, any steps that we tell the robot to do, like let's say move 500 steps forward or turn 500 degrees, I guess, it's going to execute them here, one by one, line by line. It's relatively simple, and we just have to initialize everything, actually. Now, let's see. Run up mode. So, we're going to map our motors is equal to hardware map dot. Now, it isn't DC motor. We're not going to put dot DC motor dot get. It's just going to be dot get. And you're going to see that in linear op mode, we map our motors a little differently. DC motor. But it shouldn't be too different. It's relatively simple to memorize or like to do. You can just look back on this, and if you compare them, like here's the one in linear op mode, and here's the one in op mode. Now you could see that they're relatively similar, but they basically do the same thing. You don't have to worry much about it. Just make sure to write it this way when you're in linear op mode. Actually, I'm just going to copy and paste this because I'm not going to type everything out. As you are. And just like that. Just make sure to do this. Ta-da. Right there. Lower. 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 Okay. Just like that, we've mapped our motors, and remember, just like how we initialized our motors, we also have to reverse our right motors, because remember, if you don't know why, I recommend you looking back at the explanation I made in my teleop video. Okay, let's say we wanted a robot to move 500 inches. How will we make a robot move 500 inches? How will it know it moved 500 inches? Well, the motor here, let's say this was our motor, right here. Our motor has something, a little computer inside called an encoder. This encoder, usually you find, they have specific sort of cables. They have their own cables. They look like in this color pattern. Well, mainly, let me change it up a bit. It's not light blue, it's white, just like that. Yeah. So they have this sort of color pattern, and that's usually the cable you use to connect to the brain of the robot. Let's say this was like a brain right here. Let's say this was the brain of the robot, right? You connect this to the brain of the robot, and the brain of the robot basically uses it to calculate how many steps a motor took. And a motor uses ticks, electrical steps, to calculate how many steps it took to make one revolution. And you usually find this in GoBuilda's website. GoBuilda already gives this to you. It's called encoder resolution. Now, encoder resolution just means ticks per revolution. Using this number right here, we've already found, let's say, revolution. Let's call it motor revolution. It's 537.7 ticks per revolution, right? Or per revolution. There it is. Now, with this number, we're going to try to calculate how many ticks can we get per inch. That's why we have ticks per inch over here. Let's say we're using a normal standard 96mm diameter mechanism wheel. Now, if we're using inches, we don't want to use millimeters. So we're going to go convert this to inches. Let's see. Oh, I already have it here. Okay. So 96 millimeters is basically 3.77 or 3.78 inches. So 3.78. Let's just inches. Let's just say that was a 3.78. I know it looks ugly, but we have to deal with it. Okay. So we know the diameter. We need to find the circumference of the wheel. How do we find the circumference? Well, circumference is equal to diameter times pi. Knowing this, we just plug in 3.78 inches. Say this is our diameter, and we multiply it times pi. So let's go to decimals. 3.78 times, and then if you didn't know, if you just type in pi, you just get pi, you got this number, 11.88. Let's just say it's 88. Let's round it up a bit. So C is equal to 11.88. And let's say inches for, well, the circumference of this full wheel is 11.88 inches. Knowing this and knowing this, we can calculate it using this equation. So how many ticks per one full, or if we know 11.88 inches and 537 ticks, all we have to do is put them together in this equation. So let's say F for full motor ticks divided by wheel C, circumference, right? We just plug these numbers in. This one goes in here. This one goes in here. And that will give us our T per inch. Oh. Yeah, excuse me for typing this so wrong. So using ticks per inch, we just plug these numbers in. So it's 537.7 divided by our 11.88. It was 11.88, right? Yeah. That gives us 45.26. Let's copy that. Okay. So ticks per inch for our standard 96 millimeter diameter mechanism wheel, and this case, oh, I forgot to mention, we're using a 312 RPM motor. So just so you know, the encoder resolution changes depending on the revolutions per minute that the encoder takes. So it really depends on the motor. This number changes a lot. Just make sure to check which RPM your motor is and know how to plug it into this equation. So our final ticks per inch is 45.26. And let's say ticks per inch. Knowing this right here, we can sort of calculate how many inches we want our motor to take. So let's say 45, we want our motor to move 2 inches. So we know 1 inch is 45.26, right? So we just multiply this number by 2, and boom, we have our ticks, the amount of ticks our motor has to spin for in order to, like, in order to actually spin 2 inches, or actually move 2 inches, actually. Now, if we go back to our program, we can make a function. Well, if you don't know what a function is, I recommend going to Bro Code's Java course. He explains very well what functions are. If you just want to skip to it, if you already know a bit of Java, if you don't know any Java, I recommend please learning Java right now. If this is something you're really serious about, it's difficult but really necessary. You need to learn the fundamentals in order to do this. So, moving on, we're gonna make a function that basically allows us to it calculates things for us, and it allows us to basically decide between if we want our robot to move forward, turn, or let's say in this case forward, turn, or strafe, whichever one of those, and set how much power. So let's just do public void. You can call it anything. I'll call it drive, and you should put the curly brackets. We're gonna set the power variable. We're gonna set our forward. Let's put in our int strafe and int turn. Okay, so you notice how we have our three our three variables. Actually, let's make them doubles. Double. Double and double. Okay. Notice how we have our three movements and a power variable. What we're first gonna do is, what I was thinking is, let's say we plug in a number in inches, right? What I want this function to do is, let's say I plug in the power, I plug in how many inches I want it to move, and our robot doesn't immediately know how many inches that is, so we're gonna basically plug the number of inches inside of the equation. It converts inches into ticks per inch, knowing what we already have, which, if we go here, we already have this amount of variables. We just need to calculate how we can convert those inches into ticks. So, if we already know that 1 inch is 45.26 ticks, all we have to do is, let's say, all we have to do is put in our variables. Forward times equals 45.26. And we're gonna do the same thing with the rest. Strafe is times equals 45.26. And I'm getting lazy, so I'm just gonna, well, you know what, never mind. I'm not gonna copy and paste. Times equals 45.26, right? So now that we know that if we plug in 2 inside of, let's say we wanted to move 2 inches forward, it's gonna calculate it, and it's gonna say times equals 45.26. So it's gonna calculate the number of ticks depending on the inches we input. Oh wait, yeah, just comment that. And it's the same for every single one. So now that we have this done, we basically have to stop and reset our encoders. If we don't stop and reset our encoders, it's gonna keep adding up. Let's say our starting position was 200, right? Let's say that was initial position. If we don't reset our encoders, let's say it starts at 200. Let's say let's move 300. I just want you to move 300. Let's say, I'm already at 200. So how much do I need to get to 300? So in reality, if we tell it to move 300, it's gonna add 100. It's only gonna move 100 ticks because it's already at 200. If we don't reset our encoder to 0, it's only gonna move a certain amount. It's not gonna move the actual amount. because it's already at one position. So we have to reset the position. If we tell it to reset it to 0, and then, okay, it starts at position 0 now. Think of ticks like the position inside of a motor. It starts at position 0. Now we have to move 900, right? Let's say I didn't reset. Now I want you to move 200. Now what's going to happen is the motor is at 300. We want it to move at 200, at position 200. So what it's going to do is move backwards, negative 700, right? It's going to move negative 700 ticks backwards to reach 200. You see what the problem is here? We basically have to reset our encoders and our motors to actually prevent that problem from happening and not add up, or like in this case, stay at one position. Let's say I wanted to move 2 inches using what this, let's say the encoders were already, let's say, converting it to inches. It was already at 3 inches. Let's say it was already at 3 inches, and I wanted to move another 3 inches. Let's say I plug in 3, but because I didn't reset the encoders, the computer detects that it's currently at position 3 in its encoders. So telling it that to move to 3 is basically telling it to, let's say, I'm sitting on my chair and I tell myself, sit at the chair. I'm already sitting in the chair. I don't need to move, right? So the motor, or the robot, I mean, isn't going to move. To prevent that, what we're going to do is .set mode stop and reset encoder. Now we're going to copy paste this. Now that we've set all of our, reset the encoders of all of our motors, now you see this right here, our mechanism kinematics. We basically plug this in, this same thing, into here. We're not going to set the power of our motors just yet. We are going to set the power of our motors, just not right now. So what we're going to do is basically, ticks are a position. If you want to write that down, ticks are a position in a motor's rotation. So what we're doing here is basically calculating the target position, the target we want our motor to rotate to. Set target position. So now we plug this in. You might be noticing that it's giving us an error, right? It says set target position int cannot be double. Now, the difference between a double and an int is pretty simple. One is a decimal and another is an int. But you simply can't make a double, just plug it into an integer value, right? It needs integer values. And how do we get integer values? Well, let's actually change this up. Let's say forward strafes. Let's add an S at the end of each one of these, right? And let's say int forward is equal to int forwards. Okay, and we copy and paste this. Turn. Wait, oop, that was my mistake. Okay. Strafe. There it is. Okay. Now, let me explain what I just did. We started out with double, strafes, and turns, right? It's gonna calculate the ticks, how many ticks, depending on the amount of inches we plug in, right? And now it's gonna convert these doubles, these decimals, into ints. It's actually going to convert them into ints. Or actually, sorry, I didn't explain what this was. What we're gonna do before is copy, and we're actually gonna round these numbers up. You know how you can round up a decimal? We're gonna round up these decimals, so it's gonna be whatever number I get, we're gonna round it up. Forward, turns, strafes. We can basically just set amount of ticks, it calculates it, right? It rounds it up, so it's a whole number. And rounding up that whole number, we can now convert it into an integer. And now it doesn't give us an error anymore, right? It's that simple. Here we use the math.round function. It basically rounds up numbers. Here we just convert. We take this double and convert it into a double. Into an int. Sorry, and we set it inside of the int forward, and we just plug it in here. It's really just that simple. Now, the next step we have to take right now is actually, let's copy this and let's paste this. So we stopped and reset our encoder, right? But think of ticks, they're a position in our motor's rotation. They're basically just a position. And think of them like this. Well, we've already explained how they work. That's why we have to stop and reset them, right? But now, let's say we tell it, move 200 inches forward, right? 200 inches forward. It won't do it until we tell it to run. So what we have to do is set dot run to position. It's basically gonna it's gonna tell the motors, hey, can you please start running to this position? And the motors are gonna say yeah, but they also need a power. Set power. That's why we need a power function, or a power variable input, right? So we're gonna put in power here. Copy paste this. Upper right. There it is. Okay. So this is how it should work. Stops, resets encoder, right? We tell it what's the target position we want it to move to. We tell it to run to that position, and we give it a power to run towards that position. Now, here's the thing. We can call our, let's see, now we can actually call our function, drive. Let's say we wanted to move 0.8 in power. We wanted to move 5 inches. 0, 0. Right? Here's the thing. You don't want none of these to overlap. You don't want the strafes, you don't want the forwards, you don't want the turns to overlap. You don't want those to overlap at all. If I say strafes and forwards 5 for both, what it's going to try to do is actually try to do both at the same time. And that's honestly not something someone wants, right? You don't want two things at the same time, because then it's going to get all weird and you're going to see it get all strange, right? And I know some of y'all who I think already know how to do autonomous by already be catching on into a problem. Let's say we want to move this, right? Okay. So this is how it's going to work. It's going to have a power of 0.8. The motors are going to have a power of 0.8. And they're going to go forwards 5 inches, right? It's going to go 5 is going to go through the function, right? 5 forwards. So 5 times 45.26. It's going to calculate it, round it up, turn it into an int, and stop and reset encoder, plug it in. It's going to run the motors to the position and going to set the power that we plugged in, right? And same thing here with the strafes. The only problem is it's a linear op mode. You might be thinking, what's the problem with that? Well, it basically reads the code but doesn't wait for it to fully execute. So it's like the code basically doesn't wait for any functions to finish, so we have to put it in manually. And normally you just put a sleep 100 and it should work, right? But we don't want to do that. We don't want to do that because honestly, too lazy. Like, having to put that in between every single drive is a hassle. So what we're going to do is implement it right here. Here's another thing though. We just put sleep 100, right? But we also have another problem. What if our motors were to... like we said before, a linear op mode just immediately reads everything. It doesn't wait for anything to finish. So it immediately reads this, it reads this, it reads this, and it reads this. So our motors are actually starting to run. Once it starts reading this, our motors immediately run. But then it immediately goes to sleep. What does sleep do? Sleep basically stops everything. Like, it stops every motor, it puts it to the power of 0, and stops. It completely stops. And depending on the number you put in here, and it does that for the amount of milliseconds. So 100 milliseconds, it stops. So if we were to actually run this, it wouldn't even get to go 5 inches. Like, let's say we put in 5 inches, right? 5 inches forwards. It wouldn't even get to run 5 inches forwards because it immediately just skipped through it and immediately ran the sleep function. So to do that, we have to put a while function. We have to make the program wait while the motors are actually busy running. And once the motors are not running anymore, we can actually move on, right? Stop the robot and move on to the next step, right? So what we're gonna do is put in while UL upper left dot is busy, and we're gonna copy paste this, and we're gonna put the AND operator, and UR is busy, and we're gonna repeat this for all of them. LR is busy, and LL is busy. Okay. And we don't need to actually put anything. It's gonna wait. So what this basically does is, while our motors are busy, while all of our motors are busy, the program's gonna wait. That's what it's telling it. We have to force our program to actually wait and then sleep. Because if we don't make it wait, it's not gonna wait for the motors to reach 5 inches. It's immediately gonna go and sleep. We don't want that to happen, right? So that's what we put in this while loop. At first, I thought it was kind of useless, but then when I took it out, I realized just how important this really was. And this is basically how linear op modes work. They just look per line, but don't actually wait for anything to finish, and just keep going and going and going and going. But yeah, let's say drive. Let's make another step. We wanted to move at 1, right? Wanted to move 9 inches. 7. Oh wait, no. Sorry. 0. Actually, no. 0, 0, and 10 inches. Okay. So now, let's see. This first one, forwards 5 inches, right? The next one is strafe 7 inches. And then turn 10 inches. Now, with the turn, I would say it's roughly, or not exactly 10 inches. With turn, it's a little bit weird because you can't actually know how to calculate the turn of a robot. It's kind of a random number. You can keep playing around with it. It's roughly 10 inches, somewhere around there, or it could probably be 8 or be very off the charts. It just really depends. But yeah, this is how we make a step-by-step autonomous. And with this, you can now make a list of steps your robot can take to move around and actually do things. And yeah, this was the full autonomous. I don't guarantee it working fully. There's maybe some extra steps you might be able to take, but this is basically the fully fleshed out autonomous y'all will do. And yeah, thank y'all for watching this video, and I hope y'all enjoyed this. Please sub and please support my team, Luna25662, and our socials. And thank y'all.